Hello, I'm Peeyush Mishra. I'm from NIT Calicut, and today we will be talking about iron from a metallurgical point of view. So, in this presentation, we will be talking about alloys of iron, types of iron, the uses of iron, and also about the phase diagram of iron. So, let us jump onto it. In this slide, we will be talking about the general properties of iron. So, when we say that it has an oxidation state ranging from plus 2 to plus 6, this means that it has a tendency to donate electrons, which means it has metallic nature. If it would have been minus, it would have meant that it is non-metallic and it has tendency to accept electrons. So coming to the second point, it is metallic in nature. When we say it is metallic in nature, we can see that it has tendency to donate electrons. It has lustrous surface. It exists in solid form. It has high boiling point. It has high melting point. Melting point of iron lies between 1585 degrees centigrade. So that is about it. So we can safely conclude that it is very metallic in nature and also very reactive. In fact, this 3d6-4s2 was responsible for plus 2 to plus 6 oxidation state, which allows it to be metallic in nature. Now, for the third point, when we say that it is the most common material found on Earth by mass, we mean that even more abundant than oxygen, iron is there on Earth. In fact, when we talk about the inner core and outer core, we can say that iron forms the most abundant chunk. And even when we talk about crust, it is the fourth most abundant element. So it is very much common on Earth. When we talk about isotopes of a metal, we mean to say that they will have same atomic number. When we say atomic number is same, that means the number of electrons and number of protons will be same, but the number of neutrons will be differing in each case. So 54, 56, 57, 58. And actually there is range of 54 260 for iron, but these are the most common ones, so we have taken them. And 57 Fe26, this is the most common isotope of iron, which can be seen from this. The atomic number is 26. As we had discussed earlier, the iron is very reactive. So it is very reactive with oxygen, like it is very reactive with air. So when in presence of water and oxygen, iron reacts to form a goldish, reddish brown precipitate, which is very corrosive and which leads to downfall of iron, and that is why iron has bit of limitations, which we will see how to fix them. Talking about rusting, this is an iron pillar which is present in Delhi. The best part about this is that even after standing for more than 100 years, this metal rod has not decayed. This has not corroded, this has not rusted. Before ending this, we will look at the atomic weight, which is 55.845 AMU if you want to take in AMU. And it is BCC in nature and it is denoted by Fe. As it was rightly pointed out in the previous slide, iron is very reactive, and it is no wonder that it forms many compounds. In this slide, we will be looking at the common compounds of iron. Before proceeding, we need to know that iron shows two oxidation states. One is Fe2 plus and the other one is Fe3 plus. So 2 plus and 3 plus. The 2 plus is called ferrous, while the 3 plus is called ferric compounds. So in the first four examples, we will be looking at sulfates, nitrates, oxides, and phosphates of ferrous, that is 2 plus, while the last three will be focusing on the ferric, the 3 plus oxidation state of iron. So in the first one, this is green colored crystal shaped ferrous sulfate, FeSO4. In the next one, we get a green colored crystal shaped block, that is ferrous nitrate, while ferrous oxide is a blackish colored powdered structure. And the last one, that is ferrous phosphate, it is a grayish powder which is amorphous in nature. These all are amorphous in nature. While now going with the ferric compounds, ferric sulfate, that is Fe2SO4 thrice, is yellowish in color. See, it is amorphous in nature, while ferric phosphate is a crimson orangish color, and ferric oxide is dark red, like human blood, red colored. One common feature which we can see is that these started with greenish, these are greenish, these are blackish. So these are in these shades, while the rest three, these three are in shades of yellow to orange. And the thing is that iron itself looks like a grayish metal. It is a grayish, uh, lustrous metal, but all the compounds are very much different from what iron looks like. In this slide, we will be talking about different types of iron that are present on Earth. So they are wrought iron, cast iron, steel, stainless steel, and pig iron. In fact, these are not the only ones that are present on Earth, but due to time constraint, we will be discussing only the common ones. So these are the ones. And now each of them will be having a specific slide and we will be discussing it in more detail. Now we will be looking at wrought iron. Our wrought iron was considered to be the most purest form of iron because the carbon concentration was really very less in this. And out of all the forms of iron which we discussed in the last slide, wrought iron has the least carbon percentage, which is 0.08%. So due to which it has high concentration of iron present in it, which leads to high ductility, high malleability, and great toughness. And not that just that, we also have corrosion resistance and easy weldability in wrought iron. So this is why it was used in beams. Beams are basically the building structures that are there in the construction sites due to its high tensile strength. It is also used as these black structures in old churches in the past. But now, as it was not very commercial, it has been replaced by steel, which is far more successful than wrought iron. Talking about the production of wrought iron, it was produced when pure element, that is iron, that was heated on a furnace before being wrought, that is worked with hammer on an anvil. So now we will be talking about cast iron. Cast iron is an alloy of iron that contains 2 to 4% of carbon along with varying amounts of silicon and manganese, and it also has traces of impurities such as sulfur and phosphorus. Now it improves casting performance of molten metal. What do we mean when we say casting performance? So now we can give a particular shape which we desire using cast iron. That is what we mean to say by casting performance. So that is like it can be easily casted into structures. So we can see these beautiful structures on the bridge. This all were formed, these are all given shape using cast iron, and it is very important to have a cast iron to have a good castability to form such structures. And it is not only used in bridges, but it is also used in pipes, machines, and car parts where the shape is very important to us. Now when we come to this slide, we can see that cast iron is produced by smelting of iron carbon alloys that have a good carbon content, which is greater than 2%. So after smelting, the metal is poured into a mold. Now the important point is it is not produced by hammering. We should not be hammering this. Now what is smelting? So when we heat a metal, such that the temperature goes above the melting point and it melts in presence of oxidizing agents like coke, that is called smelting. And due to this, we have relatively low melting point, good fluidity such that it can flow, and it has excellent castability. This is very important. It has very excellent machinability and wear resistance. So that is why it is used in these structures as well as these structures. Having looked to cast iron and wrought iron, we will be looking at steel in this. Now steel is more advanced and better than cast iron and wrought iron. So we will be talking about this. Now steel is an alloy of iron and carbon that contains less than 1.7% carbon and 1% manganese and small amount of silicon, phosphorus, sulfur and oxygen. Steel is the world's most important engineering and construction material. So it is used in every aspect of our life, in cars, in construction products, refrigerators, and washing machines, cargo ships, and also in surgical knives. So we can see that it is used to make pipes. Also, it is used to make wires, which we see in electrical transmission wires that are there outside our homes. And now talking about properties, it is said that they are superior to iron. And rightly so, we will be discussing them in more detail. So talking about tensile strength first. Tensile strength is the amount of stress that uh, a substance can take before becoming structurally deformed. The tensile strength of steel is comparatively high, making it high resistive to fracture or breakage. which is why a key point in it is used for its infrastructure building. Now, talking about ductility, ductility is one of the most mechanical useful properties of steel, and its ability to change shape on application of force to it without resulting in a fracture is why we use this uh, for making wires. And this enables us to use in making of different shapes of wire and structure, ranging from wires to large automotive motive parts and panels. Now, talking about malleability. So malleability is closely linked with ductility, and it allows steel to be deformed under a compression that allows this alloy to be compressed into sheets of variable thickness, often created by hammering and rolling. Now, durability. So the hardness of this alloy is high. This is what we know. So reflecting its ability to restrict strength is the thing which we know is high, and it is long lasting and great resistant to external wear and tear. So hence it is considered to be a very durable material. Now we saw that it is used in electrical wires, so we can see that it will be having good electric and heat conductivity. These properties make it very good choice for making domestic cookware as well as electrical wiring. And talking about its luster, one of the physical properties of steel is that it's very attractive. It is silvery in color with a shiny lustrous outer surface. And last but not the least, we will be talking about rust resistance. This is the main reason why we use steel and stainless steel. So the addition of certain elements which make some types of steel resistant to rust. Now stainless steel, for instance, contains nickel, molybdenum, and chromium, which will help us to improve the ability to resist rust. So we will be looking more towards rusting resistance in the next slide. In this slide, we will be talking about stainless steel. So stainless steel, like any one of a family of alloy steel that usually contains 10 to 30% chromium. Now I have mentioned minimum 10% here because it is the lowest level, but it is usually like 10%, but it can go up to 30% chromium composition. In conjunction with low carbon content, chromium imparts remarkable resistance to corrosion and heat. So this is a very important point that by addition of chromium we have heat resistance as well as corrosion resistance. And other elements such as nickel, which I mentioned here, traces of nickel, like molybdenum, titanium, aluminium, copper, nitrogen, phosphorus can also be added to increase the corrosion resistance to specific environmental conditions because it enhances oxidation resistance and also it imparts special characteristics. So now coming to the second point, we can see that the properties of stainless steel is bit like steel only, but it is bit better than stainless steel. Obviously, because it has more additions of elements, metals. That is why. So when talking about the properties of stainless steel, we can see that it has higher corrosion resistance, higher cryogenic toughness, it has high strength, it has high work hardening rate, it is very ductile, it has got a very good hardness as well as high strength, and it is it looks very attractive, and that is why we can see that this structure is made up of stainless steel, and it also requires very low resistance, low maintenance. And so in this two diagrams, you can see that this belongs to steel and this is stainless steel. Look how steel looks a bit bland while stainless steel looks more aesthetic and nice looking. That is why it is used for architectural finishes. So that is why like for architectural finishes, that means for the outward looks, we use stainless steel. And but it is not used as primary structures, not as a basic building block because it is very costly, and it is also used as cladding. Now, cladding is like any material that is used to cover a structure's exterior. Now, talking about this, this is a very famous monument that is situated in US. So this is a 630-foot high, that is like 190 meters, stainless steel that clad gateway arc, and it is in St. Louis, uh, and it is called St. Louis skyline. So that was all we had in this slide. In this slide, we will be talking about rust. Rust is an iron oxide which is usually reddish brown oxide that's formed by reaction of iron and oxygen in the catalytic presence of water or air moisture. Rust consists of hydrous iron oxides, that is Fe2O3 dot NH2O, and iron oxide hydroxide, that is FeO, OH,
and FeO is thrice and is typically associated with corrosion of refined iron. So this is the final product which we have, and this is what it breaks into the oxide which I had named just right now. And corrosion is a wide term. When we talk about corrosion in iron, we have a term called rust. Now we know that this is a redox reaction. So here we can say an iron water interface with oxygen in atmosphere. So let us understand this. So this is the anodic side, that is anode, and here it is cathode. So at anode what is happening is that iron in solid state, that is losing 2 electrons to form an aqueous state of Fe2 plus 2 electrons. Now these 2 electrons gets transferred here, and what happens is that oxygen in gaseous form plus 4 hydrogen ions plus 4 electrons forms water. So this now water goes here, this oxygen is also here, and it comes from here, and the iron is also here. So iron, oxygen and hydrogen H2O, this reacts to form Fe2O3.X H2O, that is rust. This goes in this form, and then this is how we get rust, which looks like this.
In this slide, we will be talking about pig iron. Now, pig iron is also known as crude iron. So, similar to crude oil, which is mixture of all kinds of oil and impurities, crude iron is mixture of iron as well as impurities. It is an intermediate product of the iron industry in production of steel, which is obtained by smelting of iron ore in a blast furnace. So now we can see that the percentage composition of carbon is relatively higher as compared to and wrought iron and cast iron. So it is 3.8% to 4.7% with traces of silica. This means the percentage composition of iron is relatively less in this. As it is used for synthesis of other types of iron, it is an intermediate product. And here we can see that this is how it looks. And pig iron is of a type that is used to make ductile iron. So that is why it is stored in a bin.
In this slide, we will be talking about how can we prevent rusting from happening. Now, there are four main ways how can we prevent rusting from happening. The first case we are taking is alloying. Now, iron can be mixed with many metals to form alloys. So, an alloy of iron and carbon acts as a rust resistant. It is called steel. And as we have seen earlier, we also have stainless steel. Stainless steel is formed when we have iron, carbon, we have traces of nickel and chromium, then we get stainless steel. Stainless steel is also very resistive to rust, and that is how we prevent rusting. The second way is galvanizing. Now what happens is that we have ships. Ships have iron base. Now when this iron base comes in contact with water and is also in contact with oxygen that is there in the atmosphere, it gets corroded away due to rusting. To prevent this, what we do is we add zinc over that layer, iron. So it blocks the water from iron, and that helps us to prevent rusting from happening. As iron replacing iron over and over again is a very costly process, this is a lifesaver for us. Now coming back to the third point, we can coat and paint. So coating the surface of a metal object with a layer of either paint or varnish will break the contact between the surface and atmospheric oxygen, making it consequently immune to rusting. Now the fourth point, it's very straightforward. So water is a very important reactant in this rusting for happening. Now what if we limit water? If we are going to remove water, if you're going to make it a limiting factor, the process of rusting might not happen. So this is all the things which you can do to prevent rusting from happening.
So in this slide, we will be talking about iron carbon phase diagram. Now, with point of view of metallurgy, this is a very important topic. And so we can see that when we go from y-axis, that is this line, we can see the temperature from 0 to 1535 degrees centigrade. Now 1535 degrees centigrade, as we have seen earlier, it is the melting point of iron. Okay, and at from 0 degree to 6.67%, this is the weight percent of carbon. So we can see this is increasing from here to here. Now we don't go beyond 6.67 because after this it is of no much use when we see from an engineering perspective. And similarly, when we go from above this 1535, it's not much use because it has already melted. And this is an equilibrium phase diagram, so we need to keep this constraint clear in our mind. One brief look will help us to know that there are three main phases of iron in this. So one is alpha, that is called ferrite. We have austenite, that is denoted by gamma, and we have delta, that is called delta ferrite. So when we are going from this line, okay, from 0% of weight carbon, we see that at 725 we have alpha ferrite, okay, the alpha or ferrite. And when we go above this, we see that at 1150, typically 1150, we have austenite or gamma iron. And after this, from 1150 to 1535, we have delta ferrite. So this tells us at what temperature are we going to have what kind of iron at what percentage of carbon. Now one thing more, like as we have percentage of carbon increasing from here to here, we have percentage of iron decreasing from this point to this point. Now we can see that after we are moving from 0 to some other point, suppose we are moving from this point to this, okay, like 2% of carbon, let us assume. We can see that the graph becomes very complicated at this point. And now we are not going to discuss why is this like this, because it is not in our scope of metallurgy. It's more dealt in material science. Uh, so now we can see that when we were having, like suppose for this gamma, like that is austenite. By the way, austenite was named after Robert Austin, who was a scientist. So yeah, now if you are seeing, like at this point, if we were having at 1150 degrees centigrade, at this point, like suppose we are going from this point, we will see that the change of gamma, this alpha, this ferrite to austenite, will happen at a relatively lower temperature. And this holds true for any point in this graph. So if we are moving from this point, suppose this point to this point, we will see that it will reduce even further. So that is what a conclusive evidence we have from this graph. Now one more thing, like how do we determine what phase are we going to have? So it's a very easy trick. If we are having austenite, that is this, and here L denotes liquid, so we will be having alpha plus L. I'm sorry, not alpha, this is gamma plus L. So we are going to have gamma plus L here. Similarly, when we are at this point, we are having gamma plus Fe3C, because here it was gamma and here it was Fe3C. So between this, it is FL, gamma plus Fe3C. Now this line, this gamma is a uniphase line. So we are going to have only Fe3C in this at this line, and that is why we will know one more thing about this graph. So that thing is that there are three main processes that are happening. You might have already seen here. So one is eutectoid, one is eutectic, and one is peritectic. Okay. So this is given here. Let us go to, line by line. So for first peritectic, we can see that it is going from here to here. So it is this is at 0.1. So we are seeing that delta is at 0.1. 0.1 means it is somewhere here. Will be there is a marcation of 0.1 here too, see. And at L it is at 0.5, that is here. So it is cooling at 1493 to form gamma at 0.2 percent of concentration of carbon. Similarly, for eutectic, that is from this line to this. So this line is this denoting eutectic. So this is going from L. L is liquid phase at 4.3 percentage of concentration of carbon, and it is cooling at 1150. So specifically this line to form 2.1 percentage concentration of of beta, I'm sorry, gamma, and Fe3C. Fe3C because this is ending here. While for eutectoid, we are getting this line. So it is starting at this at 0.8 percentage. So that is gamma, and it's cooling till 7 at 725 degrees centigrade. So basically this line to form alpha at 0.02 percentage of concentration of carbon, plus Fe3C because it is ending here. So you can see that these 2 points, this Fe3C is a common point in both of them because this is the ending point and this is a uniphase. Now one more thing, like we can see that like there is this juncture. On left side we are having steel, while on right side we are having cast iron. So that is basically dependent on the weight of carbon percentage. So now one more thing, for cast iron we can see that this is the lowest temperature at which cast iron can be formed. Okay, lowest temperature 1150 at 4.3 percentage of carbon. This is the most suitable temperature. So that was more about, so that was all about this phase diagrams. And the thing is, the most important point of this phase diagram is this is a unique like equilibrium diagram. So everything, all phases are in equilibrium, so there is no change in the diagram whatsoever. In this slide, we will be talking about the applications of iron. Now, I'm pretty sure that by looking at these pictures, we have got a clear idea that irons play a very important role around us, and also it has a lot of applications. So, looking at the first point, it is used to manufacture steel. Steel is a very important thing that has been obtained from iron that we have seen in the previous slides, and it is used as a building block. Not only building blocks, but also in automobiles and utensils. Now it is used to make bridges and bicycle chains, cutting tools, and rifle barrels. That is the cast iron. So it has a array of applications too. Now this is the third point is the most important point. Now Haber's process is an very important industrial process where ammonia is produced in a large scale. So when nitrogen and hydrogen combine in presence of iron as a catalyst and molybdenum as a promoter, we get ammonia. So this is very important. Now magnets have a large array of applications itself. So iron is also credited for the manufacture of magnets. Now this is a very special point. Now in our body, iron plays a very important role too. So with a lack of iron as a metal, as an element in our body, we get a condition which is very complicated. It's called anemia. So not only in the world around us, but also in the body within us, iron is required.
Now to conclude, in this presentation we learnt about the general properties of iron, the compounds that iron forms, the types of iron which we have, we learnt about rust as well, and we learnt about iron carbon phase diagram. Last but not the least, we also learnt about the applications that iron has in our day-to-day life.
Thank you.